Hi, my name is Aditya and I am the CEO of Automaski. Today we are going to be talking about the Grover's algorithm and we are going to see if it is useful or it is completely useless. But before that, a little bit about Automaski. We've been working on complexity theory since late 80s. We solved P is equal to NP in early 90s, got into quantum physics in mid 90s, and within a few years realized this universe is a simulation, and that too a linear order simulation, and that implementing physics won't require of the order of 2 to the power 3 n complexity, but rather of the order of n complexity. We had developed a rudimentary quantum computer a few years later, but only in 2014, when there were massive publications, we figured out which gates to implement and what algorithms to benchmark and test with. Hence, we implicitly achieved quantum supremacy in early 2015 by virtue of creating the most powerful quantum computer in the world with infinite precision. 2 years back, we simulated quantum gravity with a billion qubits, and 6 months back, we publicly launched our RSA 204 cracking service, available for anyone who cares to pay money and use it. Till then, it was available only to Department of Defenses and agencies around the world behind closed doors. And today, we are working on a quantum gravity computer based on causal formalism. Again, to think of it, our core quantum gravity computer has been ready for years now, and we've been playing with it and trying incremental changes. Just that we don't know how to make use of it because there is nothing published or available out there which shows how something like a quantum gravity computer can be used to solve real world problems. A small piece of advisory: please proceed with caution. If this presentation goes against your belief system, then please ignore this presentation, stop the video, and focus on things you are passionate about. If you are respectful and polite, I would love to answer any questions you might have or listen to your thoughts. Feel free to email info@automaski.com. Now, what is the Grover's algorithm in quantum computing? In quantum computing, Grover's algorithm is also known as the quantum search algorithm, which, which is basically a quantum algorithm for unstructured search that finds with very high probability a unique input to a black box function that produces a particular output. And it does so in by using just of the order of 2 to the power n by 2 evaluations of the function, where n is the bit size of the function's domain. It was devised by Love Grover in 1996. If we try to do the same operation classically on an unstructured list of bit size n, which means it can have 2 to the power n items through which we have to search, we will have to do at least 2 to the power n evaluations. Okay, in simple words, if you have a lot of items and they are not sorted or anything, they are kept in a list. Classically, on a classical computer, if you have to search for a one specific item through that list, you will have to do n comparisons. If you try to search through a unstructured, unordered list using a quantum computer which uses a Grover's algorithm, you can do this search in root n steps or comparisons. This is what basically Grover's algorithm is all about. The only thing is that we don't talk about the length of the list as n. We talk about the number of bits that are used in a problem, and therefore the problem search space is 2 to the power n, and we have to search for one unique combination in this entire search space of 2 to the power n combinations of qubit states. That is why you're seeing 2 to the power n appear in this slide, and Grover's algorithm can do it in square root n, which basically on when we talk about bit sizes is 2 to the power n by 2. This is what Grover's algorithm looks like. You have qubits on one end, and then you set up an oracle. An oracle is a black box function in a quantum computer which will amplify the right combination to the secret code, and it will minimize the amplitude of every other combination. This oracle is followed by a diffuser, and together we have to repeat these steps pi by 4 into 2 to the power n by 2 times to get the right answer using Grover's algorithm. This is where we talk about 2 to the power n by 2 times. And since pi by 4 is constant, we say of the order of 2 to the power n by 2 times steps. Now, what is the theory behind the Grover's algorithm? Charles Bennett, Vazirani and all in et al. In 1990s proved that any quantum solution to the unstructured search problem needs to evaluate the function at least 2 to the power n by 2 times. And Grover's algorithm is asymptotically optimal, which means that on a quantum computer, we cannot do unstructured search in steps lesser than these number of steps. So we can't do any better. We don't have any better algorithms for black box search. Now, like I said, you have some unknown secret value and it is inside a black box, and you have to take 2 to the power n by 2 steps to discover it. Now, Grover's algorithm is applicable to a broad class of problems. A majority of the problems we know require us to find some hidden value in a space of n bit values, which we have to find the answer to the problem we want to solve. So we represent this n-bit problem with n qubits, and we build an oracle for this problem and solve it using Grover's algorithm. We can use Grover's algorithm to crack AES, try to solve Boolean satisfiability problems, constraint solving, etc., etc. Yet, Grover's algorithm requires formidable effort. Everyone seems to forget that when n-bit space is large, using Grover's algorithm to solve problem requires a formidable effort. You might not understand this on the first glimpse, but a 256-bit key used in cryptography will require at least 2 to the power 128 steps. That's a huge amount of computational effort, which we cannot even do with any system that we have today, not including quantum computers. Now, to solve a Boolean satisfiability problem, which is the most important problem perhaps in computer sciences with n variables represented by n qubits, we would need to put in 2 to the power n by 2 effort. Considering we can already solve Boolean satisfiability problems with approximately 500,000 variables, and computers have to solve the problem beyond this range to be useful, they would have, quantum computers would have to do at least of the order of 2 to the power 25, 250,000 steps. That is like the age of the universe beyond anything that's possible today. Classically, we can do 500,000 variables, and still we believe that the actual problems that we need to solve are beyond this range, and quantum computers can never solve such problems practically. Now, Grover's algorithm is used inside 90% of all quantum computing algorithms to solve 90% of the types of problems we want to solve with quantum computers. It is the only way we know to solve such problems on quantum computers. It might be fun to try Grover's algorithm on a quantum simulator or a NIST quantum computer to solve a 10 qubit problem and claim victory and rejoice, but Grover's algorithm is completely useless for solving real world production grade problems. Congratulations. After all that hoopla, Grover's algorithm is basically useless junk. Enjoy. You take the blue pill, the story ends. You wake up in your bed and you believe whatever you want to believe. You take the red pill, you stay in Wonderland, and I show you how deep the rabbit hole goes. Remember, all I'm offering is the truth, nothing more. Thank you and hope you have a nice day.